Sound travels at 340 meters per second through air. While scuba diving underwater, a diver hears a loud noise coming from a few hundred meters away. Two pulses of sound are sent toward a receiver. Find the wavelength of a 440 Hz sound. Explain how sound energy is transmitted through the air. Sound travels at 340 meters per second through air. It's easier to say 340 meters per second instead of 343 because it makes the mathematics a bit easier. So in a location with much higher air pressure, will the speed of sound be greater, slower, or not change? Now, if we have much higher air pressure, that means that the atmosphere is more dense. And if the air is more dense, this means that sound can propagate it through it more quickly. So our answer is that if the pressure increases, then the speed of sound will increase as well. Question 2. While scuba diving underwater, a diver hears a loud noise coming from a few hundred meters away. Which is true? The sound travels more quickly than if it were traveling through air. The sound travels more slowly than if it were traveling through air. The sound travels at exactly the same speed as if it were traveling through air. Or the sound would be inaudible if it were traveling through air. Inaudible, of course, means not hearable, so it cannot be heard. So which of these make the most sense? Well, we know that sound will travel more quickly through a liquid than through a gas, right? Water is a liquid, air is a gas. So that means that if we hear a sound where both the source and the receiver are underwater, then the sound will always be traveling through water. And that means that the sound will travel more quickly than through air. So A is the correct answer. Question 3. Two pulses of sound are sent toward a receiver. Fairly straightforward, right? Now, one travels through air at 340 meters per second, and the other travels through water at 1,490 meters per second. Calculate the delay between the two signals if the receiver is 500 meters away. So in this case, we can see that the sound wave that travels through air, because it can only go 340 meters per second, won't actually be able to reach the receiver in the first second. Whereas the sound wave that goes through water will be able to reach the receiver in probably about a quarter of a second. So what we're looking for is the delay between these. And how do we figure that out? Well, distance over time. So the pulse that goes through water takes a time of distance over velocity equals time, 0.34 seconds. This formula you probably should know by now. If velocity equals distance over time, that means that simply by multiplying both sides by time and dividing both sides by our velocity, we get time equals distance over speed. So if we're going to follow exactly the same equation for the airborne pulse, how long will that one take? Well, that's right. Once again, it's a fairly simple calculation. It's 1.47 seconds. And this seems to mesh pretty well with our earlier estimate that the sound wave would take more than a second and the water wave would take much less than a second. And so what's the delay between these two pulses? Well, it's simply going to be the difference between these two. So that gives us an answer of 1.13 seconds. Question 4. Find the wavelength of a 440 Hz sound as it propagates through air at a speed of 340 meters per second. So what equation do we use here? Well, it's going to be the equation that we learned that relates frequency, which we're given here, to velocity and wavelength. And as I hope you can remember, that's going to be V equals F lambda. So we're given F, we're given V, and we're trying to find lambda. So we rearrange the equation so that lambda is the subject of the equation. Then all we need to do is substitute our values for V and F. That will give us an answer of 340 over 440, or 0.77 meters. So that means that the wavelength of this sound wave is 77 centimeters. Now this is a part A, so I'm guessing part B is going to be asking us about a different medium. So part B is asking us how long will the wavelength be if instead we're traveling through water at a much faster speed? Assuming, of course, that our frequency stays the same. So once again, we'll be using V equals F lambda, and once again, we'll be rearranging it. Lambda equals V on F. This time though, instead of substituting in 340, we'll be substituting in 1490 meters per second. That'll give us this answer, which we can evaluate with a calculator to find that our wavelength will be 3.39 meters. This means that if we have two waves of the same frequency, one is moving very fast and one is moving very slow, then the fast one will have a longer wavelength. We can see that from this first equation here. If f stays the same, but v increases, then lambda must also increase. Finally, question 5. Explain how sound energy is transmitted through the air. Now, we've talked a lot about sound waves here, but can you remember how they actually work? Well, it's a mechanical wave, right? And that should make the answer fairly easy to see. If it's a mechanical wave, then the wave travels because of physical interactions between the particles, that is, particles bumping into each other. So sound is a longitudinal wave transmitted by the collision of air particles. Air particles collide together, and this makes the wave propagate. So the source of the sound causes air particles near it to start vibrating. There's the person talking and causing particles to vibrate with their mouth and their voice box. And as they vibrate, they collide with other air particles, and that causes a sound wave to propagate. Eventually, of course, that sound wave will reach the air in front of your ear, and that will cause your eardrum to vibrate, and it will cause you to hear the sound. Right, so that's the end of the questions. In this section, we've talked about what sound is, how it works, and why it's useful. In the next section, we'll be looking at some more specifics of exactly what different sound waves might sound like.